In this manuscript, we address the broader challenge of thermoregulating building facades, not just cooling them. We present an optical design, a micropatterned directional emitter, which, when applied to building facades, enables cooling in summer and heating in winter relative to conventional building envelopes. These thermal benefits are fully passive without need of any external energy input. We demonstrate a low-cost, scalable fabrication process using common materials and well-established techniques. The thermal performance of the directional emitter is then experimentally validated under real outdoor conditions. In addition, we introduce a visibly transparent variant of the directional emitter designed for windows with a large potential impact, as windows are the biggest conduits of heat leakages in buildings. Finally, using a building energy model, we demonstrate substantial and untapped energy savings across seasons and in different cities with distinct climates. These savings are comparable to or even higher than those achieved by painting dark roofs white. In the context of global warming, the demand for cooling is rising drastically, becoming a major energy challenge worldwide. Radiative cooling offers a fully passive approach to help mitigate this issue. This well-known mechanism has been studied extensively over the past few decades. If you look at the thermal image on the left, you can see the sky appearing very cold, around negative 13 degrees Celsius, and what you're actually seeing is the coldness of the space viewed through the atmosphere. It is much colder than the terrestrial features, like buildings, for example, and therefore, this temperature difference means that buildings can effectively lose heat toward the sky, providing a natural cooling effect. This is the fundamental principle behind radiative cooling. Then, developing an optical design for optimal radiative cooling mainly involves maximizing reflectance across the solar spectrum to minimize solar heat gain, while at the same time maximizing emittance in the infrared range, where you can effectively radiate and lose heat toward the cold outer space. Although the principles of high solar reflectance and infrared emittance are well established for roof applications, considering the full building envelope makes things a bit more complex, especially because building facades actually make up most of a building surface area. So these facades play a critical role in energy loss, heat leakage of buildings. What's interesting about building facades is that they're exposed to a far more complex environment than roofs. While roofs mainly face the sky, vertical surfaces such as walls and windows still have partial exposure to the sky, but a significant portion of their view is now dominated by terrestrial features like the ground or other buildings. The complexity of this radiative environment surrounding facades presents a significant challenge when trying to develop effective optical designs. Looking at these photos taken with a thermal camera, you see the same place, the same facade, during summer on the left and during winter on the right. In the summer case, you note a very cold sky. As I mentioned earlier, it's a heat sink. It means that your facade, your building, can lose and radiate a lot of heat towards the sky to cool down. But now, if you look at the ground, it's heated by the sun and can reach temperatures up to 55 degrees Celsius. Then, the ground is much hotter than the facade, which means that while you try to lose heat towards the sky to cool down, at the same time, you gain a lot of heat from the ground. In winter, now you see that the situation flips. Now the ground is much colder than the facade, and it's actually draining a lot of heat from your building, exactly when in winter, in opposite, you want to keep warmth inside your building. If now we look at some quantitative data, you see that the typical skyward cooling potential of radiative coolers is around 60 watts per square meters. This is the amount of heat you can lose towards the sky to cool down. And if you compare this value to the terrestrial heat gains in summer, so the heat flows from the ground towards the building, you find the same order of magnitude. It means that these undesirable terrestrial heat flows greatly reduce and can even reverse the cooling potential of radiative coolers. This is the reason why these typical radiative coolers perform very well on roofs, but fall short on walls. Because okay, they cool down towards the sky, but they are limited by these undesirable terrestrial heat flows. This issue led us to wonder, what if we could design a technology that you can apply on building facades, walls, windows, that still see the sky, still lose heat towards the cold space, but at the same time prevents and avoids these heat flows with the ground, because as we just saw, the ground tends to heat up buildings during summer and cool them down during winter. To address this challenge, we propose an optical design that you can apply on building facades, walls, and windows. It's composed of a micropatterned polymer or any substrate that has high intrinsic emittance so that this horizontal facet can radiate and lose heat towards the sky. But at the same time, we coat this tilted facet, these side surfaces, with a metal nanofilm that reflectively blocks the undesirable terrestrial heat flows, so the heat gains in summer. But this high metal reflectance also means low emittance and therefore helps minimizing heat losses in winter. This design is what we call a micropatterned directional emitter. At the same time, it radiates and loses heat towards the sky, but prevent these undesirable terrestrial heat flows. We can make this optical design with a very straightforward fabrication process. First, we have to select the material. We can use very common low-cost materials such as thermoplastics, resins, ceramics. We can also reuse wasted plastics, for example. We then use established techniques widely used in the industry by companies such as 3M, for example. We first use hot pressing, where a polymer substrate is thermally pressed against the mold to imprint the desired triangular micropattern. Then, we use standard metal deposition methods, such as electron beam evaporation, again commonly used in the industry, and by carefully controlling the deposition process and the tilt angle of the sample, the metal layer is selectively applied to the tilted facet only. And that's it, we've made a directional emitter. Overall, we present and propose a low-cost and scalable fabrication process with the cost of the directional emitter around $3 per square meter, which is comparable to the white paint you can find in e-commerce. However, thinking about the visible or solar spectrum, the design is not optimal yet, because from aesthetic perspective, there is a mirror-like appearance from below due to the metallic facet, which is not desirable. And what's more, the solar radiation might significantly heat up the design as it is right now. For these reasons, we add a white nanoporous polyethylene laminate on top, as you can see here. And the nice characteristic of this laminate is that it combines strong solar reflectance with high thermal infrared transmittance. And then, we solve both the aesthetic and solar issues, but we also preserve the directional emittance in the infrared. Altogether, we propose a design optimized both in the solar and thermal infrared ranges without compromising on aesthetics. Here, the directional emitter is shown at the viewing angles that sweep from above to below the horizon, imaged with a thermal camera on the left and in the visible on the right. We note an omnidirectional constant white appearance in the visible, while in the infrared you can clearly see the transition. Above the horizon, the emitter is bright with high radiance and emittance, but now below the horizon, it becomes dim, exhibiting low radiance and low emittance. We then quantitatively investigated the optical performance of this directional emitter. To do so, we used a range of characterization techniques from thermography to Fourier transform spectroscopy. On the left, we show the emittance of the directional emitter as function of the angle from the horizon. As seen in the plot, above the horizon, the emitter exhibits high emittance, meaning it can effectively lose heat towards the sky. In contrast, below the horizon, the emittance drops significantly, indicating that the emitter effectively blocks terrestrial heat flows. On the right, we now show the spectral reflectance of the directional emitter. Since reflectance is essentially 1 minus the emittance, the same conclusions apply. We observe strong reflectance and low emittance below the horizon due to the metallic tilted facet, and low reflectance and high emittance above the horizon due to the intrinsic emittance of the polymer substrate. Lastly, over the solar spectrum, we note a high reflectance thanks to the nanoporous polyethylene laminate mentioned earlier. We then validated the performance of the directional emitter under real outdoor conditions. We compared it against the traditional white paint as a reference. We first conducted steady-state temperature test. The graph on the right presents experimental results under warm weather conditions, clearly showing that the directional emitter in dark blue consistently remains cooler than the traditional white paint in dark red. Overall, we conducted 8 experiments under diverse weather conditions. The bottom graph shows the difference in steady-state temperature between the white paint and the directional emitter. In the 6th first experiment, conducted under warm weather, the directional emitter consistently outperform the white paint, always being cooler up to 3.2 degrees. However, in the last two experiments conducted in cold weather, the situation reverses. The directional emitter is now warmer than the white paint, up to half a degree. So far, we have validated the thermoregulation performance of directional emitters in terms of temperature differences. However, this metric alone is not a good indicator of performance at the building scale. The real benefit of the directional emitter is in its prevention of undesirable heat flows into and out of buildings. To quantify this effect, we conducted two additional experiments specifically designed to measure the differential power flows between the directional emitter and a traditional white paint. In the left graph, we present the cooling benefit of the directional emitter in warm weather, reaching up to 40 watts per square meter, and in the right graph, we show the heating benefit under cold conditions, reaching up to 35 watts per square meter. These savings are fully passive without need of any external energy input. And to put this value in perspective, a standard light bulb, for example, consumes around 20 watts. The benefits of the directional emitter are up to twice this power for 1 square meter only. Overall, we show a thermoregulation potential. It means that we show significant benefits in both cold and warm weather. For now, I only showed you an opaque version of the directional emitter that you can apply on walls. However, from a building energy efficiency perspective, windows are often the biggest conduits for undesirable heat gains and losses. That's why we also propose a visibly transparent variant of the directional emitter that you can apply on windows. The concept is very similar to the design I previously showed. We find again this micropatterned polymer, but now we replace the metal nanofilm on the tilted facet by a Lowy coating that will still exhibit the strong infrared reflectance that we are aiming for, but at the same time will show strong visible transparency, which combined to the polymer transparency results in a transparent directional emitter. Unfortunately, it's not that easy because right now we have a pattern on the front side and a flat surface on the other side. With the refractive index variation, it results in the turning of the image transmitted through the sample, as you can observe on this photo. You see that the background and the transmission are slightly shifted. To solve this, we simply laminate a polyethylene film on top of the pattern to fill it so that it effectively makes the structure into a planar solid film and then restore the image that was previously distorted. You now see a transmission well aligned with the background. This variant is still at the stage of proof of concept, but presents strong potential as windows or major conduits of heat leakages in buildings. Lastly, we assess the impact of this design at a building scale. We use a custom-built and unique building energy model in different locations with distinct climates, but also with different kinds of insulation. The goal is to show the broad scope of use of this design. Then, for a residential building, when you replace a traditional white paint with this directional emitter, we found energy savings up to 55 MWh annually, which corresponds to cost savings up to $2.6 thousand a year and up to 10 tons of CO2 emission reductions. These values are significantly higher than the benefits you would get by painting a dark roof in white, for example. In this graph, we show the energy savings of the directional emitter across the different cities and the different kinds of insulation, but also split between warm and cold seasons. What's particularly interesting are the dotted black lines, which indicates the energy savings achieved by whitening a dark roof on a comparable building. It is clear that the directional emitter offers significantly greater energy savings than this dark roof whitening. Overall, we show a scalable design that achieves seasonal thermoregulation of building facades with passive cooling in summer and heating in winter relative to traditional building envelopes. We propose an architecture optimized for solar and thermal infrared wavelengths without compromising on aesthetics. We also experimentally demonstrated the cooling and heating benefit in multiple scenarios, and we modeled the impact of the directional emitter at a building scale to show substantial and untapped energy savings, cost, and CO2 emission reductions. Lastly, we also report a visibly transparent variant for windows, which presents large potential impact since windows are often the biggest conduits for undesirable heat flows in buildings. If you'd like to learn more about this design, please follow the link in the description of the video.